So many of you would not have started your NMR discussions with carbon NMR, you'd have started it with hydrogen NMR or proton NMR, in which instead of looking at the nuclei of carbon-13 within a molecule, we look at the nuclei of hydrogen-1 within a molecule. Now the fundamental principles are exactly the same. And that is that you have the nuclei of those hydrogens are spinning around, and they can be spinning clockwise or anti-clockwise. However, if you slap on a magnetic field, then all the particular protons you're interested in are going to start spinning in the same direction. And in order to get them to spin in the other direction, you have to zap them with a certain amount of energy. That energy corresponds to a photon in the radio frequency of the electromagnetic spectrum, and you can measure which photons get absorbed. Now, all of that sounds very easy, and ultimately it turns into a nice little spectrum in which different atoms, different hydrogen atoms, absorb different amounts of energy, different frequencies, depending on their environment. And so there's a table like this for the 1H NMR in your data book, just like the table for 13 carbon NMR. Now again, the same effects apply. If we start off at the top, we've just got regular old hydrocarbon protons, okay? But then as we go down and we start boxing out certain types of them, then we see that as you get more electronegative atoms near to the hydrogen, so here the hydrogen's got nitrogen, oxygen, 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 aromatic ring that we'll come to in a minute, halogens, oxygen, 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 down here oxygen and oxygens. The more electronegative atoms that are near to the hydrogen, well then that hydrogen nucleus is less shielded by those electrons, and so it requires less energy. We box this little group here in blue. These are the hydrogens associated with the aromatic rings, and that's because those delocalized pi electrons in the benzene ring means that these protons are again less shielded. The hydrogen nuclei are less shielded. And so you have this nice little table, just the same as we saw with the carbon-13. Now you might have immediately noticed one big difference, and that is that the carbon spectra, the ppm, could go from 0 to over 200. With proton NMR, they go from 0 to 11 when you're dealing with most organic nuclei. So that means that the proton spectra are far more squished together. So you might say, well, why do we use protons so much more than carbon? And the answer to that is that when we're looking at the carbon-13, we're looking at 1% of the carbon atoms within a given sample. When we're looking at hydrogen-1, we're looking at 99% of the appropriate protons within a given sample. Now that massive increased abundance associated with the proton leads to quite a few things that we're going to discuss as we go through this movie. But first of all, let's just pretend like we're thinking about this just like carbon-13. There are the different shifts. Let's look at a proton NMR. And I'll start off looking at this one for chloroethane. So we've got two types of hydrogens in there, the ones labeled in blue and the ones written in green. Spectrum looks like this. So we got two types of hydrogen. So we're seeing two bumps. Okay, we got this bump here that's at about 3.6 or so, and this bump here that's right about 1.2. Now let's match those up to our nice little chart. First of all, the green protons are on a carbon that's also bonded to a halogen. Corresponds to this. There's a carbon bonded to a halogen, in this case chlorine. We're looking at the hydrogen on that. We expect that shift to be between 3.1 and 4.3, and we said it was about 3.6. And so that first hump there corresponds to the green protons, the ones on the carbon bonded to the chlorine. And then, of course, the other hump must be the three hydrogens here on the carbon that's not bonded to the chlorine. It's just bonded to another carbon. And so that's going to be that type of shift, exactly as we see should be somewhere between 0.1 and 2, and we said it was what, at about 1.25, something like that. Okay, so absolutely no fundamental difference in the general principles between those that we studied for the carbon-13 and those that we're now going to continue studying for the proton NMR. Different protons in a molecule give different shifts on the spectrum because their different environments means that they absorb or emit different energy photons.